Thank you very much. As Joel said, my name is John Pendleton. I'm the area sales rep with EOS here in North America, responsible for the central region. And today we're going to be talking about additive manufacturing and it being a new way forward for actual production. To give you a brief overview of what we're going to hit on today, I'm going to give you a brief background on EOS, where we come from, where we're going, an overview of our technology and what makes it different from some of the other 3D printing methods out there, some challenges as you're moving into production, how to develop and implement a successful additive manufacturing program, some impacts that will then have on the traditional supply chain, and then wrap things up with some real-world case study examples. So EOS has been in additive manufacturing for 30 years. We were founded in 1989 by Dr. Hans Langer, who is still the founder and owner of the company. We are privately held, not publicly traded. We are primarily focused on medical, aerospace, and general industrial applications, as they've been the widest adopters of the technology so far. But with some advancements over the past few years and what we've got cooking in the pipeline, over the next 2 to 3 years, we're going to see some really big productivity jumps and lower cost for parts that are going to bring production into automotive and consumer segments as well. We are solely focused on powder bed fusion, which Bob hit on a bit earlier. I'll dive into that here in a couple slides, but we do offer both metals and polymers. And lastly, we have a group of applied application engineers on staff called Additive Minds that transfers our 30 years of experience to our customer base, which we'll hit on as well in a little bit. So looking at EOS, we are not just a provider of additive manufacturing equipment. It's really part of a larger ecosystem that our founder and owner, Dr. Langer, is invested in. So that is a holding company that's made up of EOS, who provides additive manufacturing equipment and applied engineering services, a company called Scan Labs, which makes the laser scanners for our systems as well as a majority of our competitors' systems as well. And then AM Ventures, which is a venture capital arm that invests in startups within the additive manufacturing space that either support EOS's core technology in powder bed fusion or invest in something that could ultimately disrupt EOS and become bigger than what we are today. Just hitting on it briefly, within EOS is our Additive Minds Applied Engineering Group, company AM Metals that develops new powders and processes to process those. AMCM is a really cool company. They're taking either stock EOS machines and customizing them for specific applications, so things like more lasers, bigger build envelopes, hot machines to process tough to weld materials, and a couple powder companies on the polymer side as well. ALM is a wholly owned subsidiary of EOS based in Temple, Texas. They're our custom polymer material division, not just for North America, but for the rest of the world. They'll take your part requirements and tweak the powder specifications on the polymer side to achieve different results. And then on the AM Ventures side, we've got a couple different companies as well. So Centrotech makes a desktop SLS machine. 3Year Mind is an MES ERP system designed just for additive manufacturing. Elementum 3D creates custom metals, a lot of metal matrix composite material where you're adding ceramics to tough to weld materials to process them in our equipment. And then lastly is Dimension. They make post-processing equipment for the entire polymer process chain. So successful AM integration requires partners along the whole way. As I mentioned before, we're experts in metal and polymer additive manufacturing. We're not experts in CAD software, post-processing. So we work with and identify partners along the entire process chain so we can really develop an entire solution package to fit whatever types of parts you're going to be producing. So we're working with established companies like Autodesk, Siemens, Dassault, Materialize for the CAD and data preparation, SAP for integration into your ERP and MES systems, post-processing companies like Extrude Hone to get better surface finish on external and internal features. software companies like Atlas 3D, which we're going to be talking about later, Additive Works, these are process simulation softwares, and then different machine technologies as well. So EOS is a global company. We are headquartered outside of Munich, Germany in Kreiling. We've got actually around 1,400 employees, most of which are based in our Kreiling headquarters. We're about 175 here in North America. We've got offices in 15 countries, distributors all over the globe. We've got over 3,500 systems installed around the world. About 50% of those are metals and the other 50% of polymers. We're a bit metals heavy here in the United States. It's about 70 or 60-40. So North America is our largest single market for EOS when you break it down country by country. About 35% of our global sales are here in the US, which is pretty shocking when you look at the traditional CNC market. When you look at CNC machines, about 1 in every 2 machines ship to China, and the other machines shipped somewhere else in the world. For additive manufacturing, 1 in 3 machines is coming to the US, so that really is kind of a testament to bringing manufacturing back to the US and focused on investing in high-end technologies. EOS is a company here in the US. As I said a minute ago, we're about 175 people. Over 50% of those people are customer facing, so field service engineers, tech support, and things like that. And we provide all of our own services from installation training. We'll get a bit into that in more detail here coming up. We've got 3 locations. Technically, our corporate headquarters here in the US is in Novi, Michigan, just outside of Detroit. We've got another technical center down in Pflugerville, Texas, just outside of Austin. And then we've got our ALM facility up in Temple, Texas, that does all the polymer development. Kind of hit on this already. So North America is about 30% of our global sales, Europe and the rest of the world 50%, and the Asian Pacific market is picking up steam at about 20%. So our mission is for additive manufacturing, or for EOS to be the leading provider of additive manufacturing solutions, and we see our systems as being essential to the digital factories of the future. And our vision is for additive manufacturing to play a key technology, or to be a key technology for advanced industrial production now and looking forward. So, as Bob mentioned, powder bed fusion encompasses both selective laser sintering on the polymer side and direct metal laser sintering on the metal side. Fundamentally, the 2 processes are the same in that we're using an energy source to melt layers of powdered material together. There is a fundamental difference between the 2 processes. SLS is what we call a hot process, meaning we're heating the entire build chamber up to within a few degrees of the melting point. And then we're using a much lower powered laser to actually tip the material over the melting point and solidify that layer. The metals process is a cold process. Relatively, you can heat the build plate up to certain temperatures, but you're using the laser, a much higher powered laser, to fully melt each layer to the previous layer. And the process is pretty simple. There's a recoater blade that drags a fine layer of metal or polymer material across a build area. You're going to have a dispenser bin on one side and an overflow bin on the other. The recoater blade is going to drag that layer of powder across. The laser is going to fire, melting that top layer, and then we're actually going to penetrate 3 to 4 layers previously, which is very important on the metal side to ensure that you're getting well-defined part properties and no porosity in your parts. And so the build platform is going to lower by the thickness of 1 layer. On the metal side, it's anywhere between 20, 80 microns, depending on what you're processing. And then on the polymer side, it's going to be between like 80 to 180 microns, again, just depending on the material. And that recoater is going to go ahead and drag another layer of powder across, and the process is going to repeat until the parts are finished. Once it's done, pull your parts out. The SLS side, as I mentioned before, is a hot process. So there are no need for support structures, so you can build the parts the entire Z-axis height. And then you dig the parts out kind of like an archaeological dig out of the remaining powder. And then you go ahead and take those out for post-processing. The metal side, you are essentially micro-welding every layer to the previous layer, and you need a starting point for several reasons. The first is to give the part a solid foundation to build upon, but more importantly, it acts as a heat sink, because there's a lot of, you're putting a lot of energy into sometimes a very small space, and you need to take that energy away. So you have to remove those parts somehow. Again, I think Bob mentioned you can use a bandsaw wire ADM for tiny little parts like that bottle opener. You can just crack it off from your hand. So looking at our product portfolio on the polymer side, we've got a wide range of systems that can fit specific needs or that you can grow with as you're moving from, say, out of prototyping into production. And some of these machines are specialized to process higher temperature materials. So when we're looking at aerospace, they want to do some funky materials that are what we consider higher temp in the SLS side, but are really in the mid-temps and the peaks and pecs and things like that. So we have a couple of systems that are designed to process those materials up to 300 and 385 degrees Celsius. And one thing that's kind of cool I want to note is the Integra P400. So all of our machines have traditionally been designed, developed, and produced out of our facility in Preiling in Meizach, Germany. But over the course of the last few years, through some acquisitions we made, we have started to develop and commercialize our own polymer laser sintering machine that we've designed at our facility down in Austin, Texas. That is going to be made here in America, and kind of gives kind of a testament to the North American culture here that we want to stay on the forefront of innovation, and our corporate headquarters kind of gives us a little bit of leeway to do things differently and build a product that addresses specific needs for our region. Looking at the metal side of things, we've been doing DMLS since DMLS was invented in 1994 when we commercialized the first metal system ever. That was the M250. And there's a lot of different terms to describe DMLS or metal additive manufacturing, powder bed fusion. The reason why we trademarked direct metal laser sintering was because back in 1994 we were using low power lasers. And we were doing just that, just sintering the powder together. There's a bit of porosity, but over the years we introduced in 2004 the M270, which had the first fiber laser, and then really went from sintering to melting. And then in 2009 we introduced the M280, which went from a 200 watt fiber laser to a 400 watt fiber laser. That increased or decreased build times and increased the number of materials we could produce, things like titanium and aluminum. And then in 2014 we launched our M290. So as you can see, there's been a slow evolution of the technology and the development and really the robustness of our systems. So we're not on our first or second generation here. When we look at our medium-sized machines, we're really on our fourth and going into our fifth and sixth generation systems. Similar to the polymer side, we do have a full suite of machines that you can grow with as you're developing your applications and moving into different types of applications and products. So we've got a small frame M100, ideal for dental coatings and bridges, things like that, or even small medical implants. Material on R&D, perfect. And you can grow into the M290, 10 by 10-ish build chamber, up to the large M400s, which have essentially a 16-inch build envelope with an option for a single 1 kilowatt laser or 4 400 watt lasers. So moving towards manufacturing, giving you some insight into where our customers are currently at, where the industry is at. So over the last 30 years or so, the industry's been extremely focused on rapid prototyping. It's an obvious win when you invest in the technology. It gives you some great tools for product development and things like that. But over the last 5 years, we have seen a very strong push towards actual production. Just looking at the industry as a whole, back in 2015, we were at $5.2 billion, including machines, services, materials, things like that. And some analysts are projecting the industry to be $14 billion by 2020. It's pretty rapid growth. It's typically around 20-25% year-to-year growth, and we're growing at a similar pace, which is great to see. Metal AM is really driving the growth, especially here in the United States, with aerospace and medical leading the way. If you just look at those two industries, there are high-value parts on every plane, and medical implants are also high-value parts as well. There's a lot of opportunity for mass customization in the medical space, where you can take CT scan data, reverse engineer that, and then 3D print a hip or a knee implant that matches your specific body structure. Leads to better outcomes and things like that. And then of course on the aerospace side, every ounce on a plane translates to millions of dollars in fuel for the life of that airplane. So if you can cut even grams here or there, it's going to generate massive savings for them. But we're also seeing additional growth in areas like high temperature polymer applications, so replacing metal parts with polymer parts and things like that, which is obviously going to lower the weight. And we're going to get into some other areas of where you can apply it, but there's always opportunity for more growth. One of the limiting factors in the industry right now is standards, which I think everybody will agree upon. So as the ASTMs and those of the world finally put in place standards, we're really going to see some wider adoption of the technology. Education is obviously a huge problem. I think that everybody's looking to address, including us. Operators are few and far between that have any real experience. So as Bob mentioned, if you find a good one, make sure you hold on to them. Material development has always, and the range of materials that are available has always been a limiting factor as well. But as I think the guys from Pendleton will talk to you a little bit later here, there's a ton of activity going on around bringing new metals and polymers to the market, and is really going to drive a lot of the applications moving forward and what's going to be possible. And then, of course, machine speed, ease of use, industrialization, making sure consistent uptimes and things like that. I'm going to go ahead and skip over this slide because I just talked about a lot of it. So the advantage of additive manufacturing. There's really three main advantages to additive manufacturing when you're looking at identifying production applications. Of course, complex structures are the best thing to look for. Incorporating lightweighting techniques like topology optimization, lattice structures, things like that. Essentially, if you can cut something out of a block of steel, it's cheap and it's easy, do it that way. If you start looking at things that require fifth axis and a lot of setups and tool changes, that's when additive manufacturing can really be a good solution to your problem. Customize individual objects. Again, we're seeing this a lot on the medical side, but we're also doing this a lot in the automotive industry as well, which I'll get to. A really cool project we're doing with Mini over in Europe. And then functional integration and part consolidation. So we always talk about designing a part for additive manufacturing for its intended use rather than for manufacturability, meaning design the part for what it's going to do and not how you traditionally cut it out of a block of steel or mold it. This really allows you to leverage the full potential of additive manufacturing and do things where you take, in this case, a 32-piece assembly and reduce all those components into 3 parts, and that's going to have not only a drastic impact on your supply chain, but you're going to increase part performance and part life because you don't have weld seams and raises that could fail over the life of the product. So as I mentioned before, we've really been focused on prototyping for a number of years, but today we are seeing a select number of production applications where we're focusing on part quality, process robustness, and trying to optimize the cost per part. And then over the next couple of years, as we're ramping up into production with our customers, you really need to focus on quality control, differentiation, the total cost of ownership. We're doing things around automation and technology integration into your traditional manufacturing floors. And I think it's important to note that global leaders are investing into additive manufacturing today and are leveraging it for production throughout this wide range of industries, from medical to automotive, aerospace, and then of course our local service providers that are a great resource to use while you're trying to figure out whether or not the technology is a good fit for different applications. So one example I wanted to talk about was a very cool project we did with Premium Aerotech over in Germany, who's a fully owned subsidiary of Airbus, and then Daimler, which is the parent company of Mercedes-Benz. The goal of this project was to completely automate the entire process flow of the additive manufacturing process. I had a really cool video that would show this much better than I can talk to it, but unfortunately it doesn't work on a Mac. But anyway, the result of this project, after about a 1.5 year long partnership between the three of us, was a completely automated metal additive manufacturing cell where there's automated guided vehicles moving build plates in and out of the machine over to post-processing to inspection. All the powder is delivered automatically to the machine, and then out of the exchangeable frames that move between these different pieces of or different processing stations. So if you want to check this out, go to YouTube, type in EOS GmbH, and it'll be right there. But of course, with production comes qualification. It is a step that can never be overlooked, as it is absolutely critical to ensuring your parts are meeting the properties you define. We go along TRL levels like many organizations do, and it's important to certify your process along the entire way, and it's one area that EOS can assist you with, is setting up your operational qualification, your performance qualification, and then ultimately the statistical process control. And all of this is a critical step as you're building a successful AM program, which leads me into our Additive Minds group. So Additive Minds is essentially a group of over 150 application engineers across the globe, with about 30 of them here in the US. And the sole purpose of our Additive Minds team is to transfer our 30 years of experience to our customers and try to get their applications up and running in as short of amount of time possible. And the way we do this is, they call it a consulting approach, but it's really not. They're really joint development projects where we work with our customers to, this is a very kind of boilerplate way of saying it, but find your application, develop those applications, certify and ramp the production, and then optimize and scale your production. And then the last topic that's not on there that we're now focusing on as well is digital integration. So how do you take your additive manufacturing machine and loop it in with all the other processes that have to go on with delivering a good quality part? So in the Find Your Application area, this is where we do just kind of workshops to scan product portfolios and identify parts that have high value and potential for additive manufacturing. Developing those applications, where can we redesign parts to leverage the benefits of additive manufacturing and make the program more successful. Certify and ramp the production, so like I just described, doing the operational qualification and performance qualification of the part, and then ultimately having statistical process control along the entire process chain of your production. So how does this have an impact on supply chains? So we're going to have a couple different cases here that makes additive manufacturing a viable tool for production today. So as I mentioned before, part consolidation, simplifying assemblies, reducing assembly times and the costs associated with them. Designing for function, again, we need to design in the parts for their intended function rather than for manufacturability. So if we look at this satellite antenna bracket down here at the bottom, the original design, a bunch of sheet metal welded and riveted together. Then we've got the topology optimized design here in the middle, and then the reduced part. I have the statistics somewhere on what this is, but on the number of parts reduced and the weight savings, but I can share that later. Decentralized manufacturing is a big topic we're working on right now. So putting machines closer to their customers for several reasons. Obviously, you can reduce the supply chain costs and the logistics nightmare of trying to source parts all over the globe, which also leads you to spare parts on demand. It's easier said than done, to be honest with you, but there have been a number of very successful programs that implemented spare parts. Obviously, warehousing millions of components is very expensive, time-consuming. Again, it's a logistical nightmare. So if you can somehow figure out a way to digitize your product portfolio and only produce what you need when you need it, there's huge time and cost savings there as well. Eliminating high minimum order quantities. There's nothing worse than contacting a supplier and you need 5 parts and they're telling you, you got to order 100 of them. And you got to overpay for those, and then you got to stock them somewhere. Shorten delivery, eliminate overproduction. Again, only producing what you need when you need it. Fast repairs and upgrades. This is something I don't think is talked about enough. One of the great benefits of our metals technology is you can build on top of existing components. So on the right-hand side, this is an example from Siemens. These gas burner tips wear out over time. And they used to take several months to repair, and now Siemens brings those in-house. Wire EM's the top portion that wears off, and then throws it into our machine and rebuilds the wear component right on top of the existing piece. And this also opens up entirely new business models for Siemens as well, because they're constantly trying to be innovative in their turbine designs, and additive manufacturing allows them to upsell their customers on new designs for their existing turbines. So it's an entirely new revenue source for them as well, but it also saves their customer money because they're just upgrading an existing piece of equipment as opposed to having to invest in an entirely new one. And then of course, additive manufacturing can be lower cost versus traditional manufacturing when you're looking at the right application. So one that project I just mentioned that's really cool is the mass customized example from Mini Yours. So this is a true additive manufacturing production program at Mini. You can go onto the Mini website and completely customize the dashboard inlay, and then these little decorative pieces by the blinkers on either side of the car. To whatever you want. So there's a user interface on their website where you can go in and put your name in there. You can put a skyline, and Mini's going to actually, is actually 3D printing these and delivering them to a customer in about a week. Great thing about this, it's entirely digital, so there is no inventory, and it's as I just mentioned with Siemens, it's an entirely new business model for Mini. So you look at the automotive industry, everything you buy from them is either from a dealership or from a third-party store. You're rarely, if ever, buying anything directly from the automotive OEM themselves. But in this case, Mini/BMW is actually going to be the one charging your credit card, and they're the ones actually delivering the parts. So this is an entirely new business model for Mini that's completely changing the way they've traditionally gone about selling products to their customers. So looking at some further examples, one cool project we just did with Joel and ITAMCO, or that they're working on right now, is replacing Vietnam-era runway mats with new innovative design, looking to lower the weight, easy development of the runway mats and low wear. And what they ended up using was a new 316L powder we developed with GKN. Traditionally, a lot of the metal powders are atomized using a gas or plasma atomization process. This is a water atomized 316L, has a much wider powder particle size distribution, which makes the powder a lot cheaper. But we're also going to sacrifice a few percentages in density to drastically increase decrease the build time. So something that would typically take, say, 20 hours to produce using this new powder process, it may take 10 or less hours. And this was a joint project between ITAMCO, Atlas, Purdue, and ultimately delivering components to the U.S. Air Force. A couple more examples before I wrap things up. So this is a Class 1 critical flight hardware for the Ariane Group's next generation rocket engines that are for the European Space Agency. Traditionally a 240-piece assembly that had every one of, or it's not up there, but every one of these fuel nozzles inside of that housing had to be welded and brazed together. Obviously that's 240 weak points that could fail when launching the rocket. They were able to simplify that assembly from 240 pieces into one part. Traditionally took 3 months to produce. They're able to additively manufacture this part in 3 days. And I think the costs are something like 50% lower once you take the entire process and supply chain into account. Tons of applications on the medical side for metals, as I mentioned before, spinal implants, knees, hips, things like that. One of the most growing areas we're seeing right now are for orthotics and prosthetics. This is a cervical orthosis, but you can also do mass customized orthotics and prosthetics, really putting the power of the design into the end user's hands. So with prosthetic legs and things like that, amputees tend to really want to take control of the design of their prosthetic. I mean, if you think about this, it's a very sensitive topic to begin with. But then if you give them the power to ultimately create the prosthetic they're going to be wearing every day, they feel much more comfortable with the product, and ultimately gives them a higher quality of life. This is a example of tooling. So we're seeing tooling used in a wide range of industries, from injection molding. One of the biggest ones that's growing right now is high pressure die cast tools and inserts. This is an example for tire molds. Traditionally, you could only do the tire sipes, but now we're doing full mold segments. Very complex geometry, very difficult to produce, but doing it additively is way quicker, and the design can be much more intricate. As I just mentioned, high pressure die cast tooling. These additively manufactured inserts run much cooler than the conventional method, so you're able to put the cooling lines closer to the surface of the mold. Ultimately reduces hot spots, warping, things like that, but also reduces the cycle time and overall increases the quality of part that's coming off of the equipment. Spare parts on demand. We did a very cool project with Daimler as well. They're producing over 150 part numbers additively for their EvoBus division that are being sourced around the world for spare parts for the buses. And lastly, Lindy. This is a glass treatment burner. Traditionally, it was manufactured as 15 parts. In this case, they're able to additively manufacture it as a single component. They're also able to incorporate water cooling lines in there that improve the life of the part as well. So with that, I will hand it over to my next presentation.